Right, so this is the motion problem lecture. This will help you figure out how to do these kinds of problems. So on this piece of paper, I want to make, first off, just two little alterations here before we get started. I made these changes in a file, but it didn't come through in this print job. So if you could please change these delta x's to distances, that would be helpful. So to start things off, I just want to talk briefly about the process and ways that can kind of help you figure things out. So this part up here, I'm going to kind of skip this, but I do want to just kind of mention a little bit what it's trying to talk about. And that is basically units. Units are really useful for figuring out what kind of variable you're working with. If you see a meter, meters are going to mean that you're looking at a distance. Okay. Seconds are going to mean you're looking at a time. Meters per second squared means that the numbers attached to is going to be an acceleration. And then finally, meters per second can mean two things. It can either mean, in most problems, initial velocity, which is VI, by the way, or it can mean final velocity, which is VF. Okay, so using this idea here, we can kind of hopefully figure out what each number means. And just keep in mind, remember the phrases stopped and at rest, because those ones are important for figuring out these velocities down here. Okay, so when we're looking at problems, the first step we're going to be basically looking at is going to be identify variables. I'm going to write my variables off to the side and use problems like over in this area, just so that we can kind of have an easier access to them. Okay. Once we've chosen, once we know what variables we're working with, we need to choose. Oops, there we go. An equation. Okay, we have three equations over here that we're using today. We'll use one of these three equations for solving a problem, and then step 3, we're going to plug in, which is usually pretty fast, but be careful in this step. People do make mistakes. And then we're going to solve, which sometimes means we are going to be using algebra. Okay? So, let's take a look at a problem. This is probably the best way to kind of look at stuff anyway. So here we have a frisbee. It flies across the ground with initial speed of 16 meters per second. As the frisbee flies, it slows down from the air, experiencing an acceleration of -2 meters per second squared. The frisbee lands after a flight of 5 seconds. How far did the frisbee travel? So let's start pulling some things out here. All right. First off, right here, that is a number with a unit. So meters per second will either mean initial or final speed, and they say initial right there for us. So I do right off the bat figure out that this thing is a 16 meter per second initial velocity. Okay, here it says it slows down from the air at a rate of -2 meters per second squared. Okay, be careful, that negative there is important because it means the thing is slowing down and not speeding up. And then finally, we get a time from this 5 seconds over here. So that's our knowns. Now the final piece over here is going to be asking us what we're looking to solve for. So in this case here, how far means we're looking for a distance. Okay? Now, that is step 1. We are all good with our identification of variables. Our equations now, we have to choose one. And if you look at what we know and the equations over there, there's basically 2 general ways you can look at how to do this. We want to look at our 4 variables that we have, the 3 that are given to us, and the 1 unknown, and we want to make sure all 4 of those variables pop up in our equation. Another way you could look at it too is look at the variable that you don't have. In this case, we're missing VF. And we can look for an equation that doesn't have VF. And that's another way we can go about looking at which equation we want to choose. Either way is fine. So if we look up here, right here, that has VF, so I kind of don't want that equation. And if you notice here, this equation here is missing distance. So we can just kind of keep that in mind when we're looking at that thing. Over here, this is distance equals 1/2 VF plus VIT. There's that VF again. We don't want that one. And this one is also missing an acceleration in general. And then finally, this equation here, dVIT 1/2 A T squared, that's all we have right here. That's perfect. And this one is also missing the VF, so we can use that as shorthand when we come back to this equation in later problems. So I'm going to copy that equation down here in the center of my paper, just like this. VIT plus 1/2 AT squared. All right, and at this point, I'm going to plug in. So distance is unknown. VI is 16. And when I plug in, I just put things in parentheses. There's an implied thing, multiplication between the parentheses here, so I hope that makes sense. If you have questions, you can always ask me at some point. 1/2, A is -2, and T is 5, and don't forget the squared up there. And in this particular question, we are quite lucky because the equation is already solved for us. So all we need to do is plug into a calculator. So I got my calculator right here, and I just plug it in like it says right on this equation, and we should be good. So 16 times 5 plus 0.5 for 1/2 times -2 times 5 squared. And plugging that in just like that, we get an answer of 55 meters. And that is our final answer. So there is our first kinematic problem. Let's go on. So in number 2, we have a multi-stepper. In this question here, we have a car that's moving down a street at a constant velocity of 20 meters per second, which is going to be about 48 miles per hour or so. A child suddenly runs into the street 60 meters in front of the car. And we're going to try and figure out if the child gets hit by the car. Let's hope not. So sometimes I'll draw things out. You don't have to draw things this unit, but I just kind of like to draw here just to kind of keep our perspective. All right, and I apologize, my drawings are always awful. As you can see, this kid is much bigger than anything than the car. But we do know from this distance over to the kid, that is 60 meters at this point. Now, we want to be careful with these kinds of questions because the known that they're giving us here isn't one we actually use in an equation. We want to try to figure out and check against that number. So let's start looking at the problem now. So in A, it's asking us it's telling us the driver takes 0.75 seconds to react. How far will the car go before he applies the brakes? So there's kind of two ways we can go about doing this. We have a velocity here of 20 meters per second. Now, the problem with this one is we don't know if it's an initial or a final, so we'll come back to that one. And then they also tell us here the car is traveling 0.75 seconds before the guy's able to react, because there is that reaction speed element to any kind of car driving. And then finally it asks us how far does the car go before the brakes are applied. So we're looking for a distance. Now, we kind of have an option here. We can kind of either look at this equation here for a constant velocity, or we can try and use one of our other acceleration equations. Since this is a constant velocity here, we can use this equation. Oh, I just messed that up. V equals. Or we can also kind of conceptualize this as being VI and VF. Since it's not changing, it's kind of both. Which in this case here, we're missing acceleration, So without an acceleration, we're looking at that equation. So you can solve this equation using either one of these two equations. Both will get you the same answer. Perfectly fine. But let's use this one for my purposes. It should work out just fine. So V is 20, T is 0.75, and D is unknown. So unfortunately this time we do have a situation in which our equation is not solved for the variable, but this one's not too bad. We have a division here, so I want to do the opposite. So multiply both sides by 0.75, which cancels there. And then over here, that multiplies. And what we kind of find out then is that distance is equal to 15 meters. So at the end of A, if we had 60 meters before the child, this is now 45 because the car has traveled that far. As we press on, letter B asks us if the brakes accelerate the car at -5 meters per second squared, how long will it take the car to stop? So here, that's giving us an acceleration. Once again, we want to be careful of that acceleration because that negative sign is very important. It's the difference between the guy hitting the brake and hitting the gas pedal and speeding up towards the child. And that's not what we're looking for. All right, T is unknown, so I'll put that one there. And now we're kind of stuck, to be honest, because they don't tell us anything else. If you think about it, though, at the end of the time period from letter A, we know the car is traveling at 20 meters per second. And since this time period B begins right at the end of time period A, we can kind of infer that the VI is also 20. But we are still missing a known. We are still missing something that we would need to solve this, because whenever we're looking at one of these equations, we do need three knowns. And if I take a look here, I see that word stopped. And if you recall, back in the beginning, stopped often means that one of our variables, either initial or final, is 0. And in this case, because we're coming to a stop, it does imply that our VF is 0. So if you look at the knowns we currently have, we are missing distance. Distance is the thing that we don't care about and we don't know. So if we take a look at our equations, this right here is our equation that's missing distance. It also has VF, VI, A, and T, so that appears like it's the equation we want to use. So let's copy that down. All right, and plugging in, our VF would be 0, our VI is 20, A is -5, and T is unknown. Unfortunately, again, we have to do a little bit of work here. We can't just plug into a calculator. So looking at this here, the 20 is the addition piece. I want to look at that first since it's the most right on our order of operations, our PEMDAS. So I'm going to subtract 20 from both sides. That cancels there. And I'm left with -20 equals -5t. Dividing both sides by -5 to get rid of this multiplication. This will cancel over here. And we're left with 4 seconds equals t. Okay, and that is our final answer for this part of the question. Now, if you scroll down, there will be another video here where we'll probably solve C and also number 1. So go down there and continue the lecture.